start lecture 33. The course is corrosion protection methods. For the last few classes, we have been discussing on the change in electrode potential or the metal potential, which is to be protected, of course, either cathodically or anodically. We have only talked about cathodically changing the potential. So that means taking the potential downwards from the stable potential. And we could see that that can be possible, and the corrosion rate or corresponding anodic current density or dissolution rate can be reduced for the metal, and that can be possible via two mechanisms. One is, of course, ICCP, where the metal which is to be protected can be connected to the negative terminal of a DC power source, which is external power source, and that method is ICCP or impressed current cathodic protection. And then we have also seen that for the sacrificial anode, so there also the metal is to be protected, that metal is made into a cathode, or other way around, we actually take the potential down, same cathodic polarization, where the active metal dissolves and the noble metal is protected, and this active and noble metal in that particular solution, as per the galvanic series, they are galvanically connected, just like iron and zinc or iron and magnesium. So iron sits on the top of that particular series, galvanic series, in a particular solution, let's say hot water solution or NaCl solution, where zinc stays at the bottom or magnesium stays farther below. Then these two active metals can dissolve itself, and due to that it will supply electron to the steel, and the steel will be made into cathode. Now we will talk about another interesting approach, which is called anodic protection. And in case of anodic protection, we will make use of anodic polarization. So let us look at that particular mechanism, how it works. So today we will talk about anodic polarization and corrosion protection. If we consider active metal and if we look at mixed potential theory, let us see what happens if we increase the potential. So anodic polarization means increasing the potential from the stable potential. It can be either equilibrium potential or corrosion potential. So let us look at that particular aspect. Let us say zinc in HCl, and let us say it is a pure HCl. So only hydrogen evolution is the cathodic reaction and zinc dissolution is the anodic reaction. So if we look at the mixed potential theory, this is log I, let us say it is ampere per centimeter square, and this is voltage over potential. Now let us consider this is at 0.76 minus volt, and this is 0 volt for hydrogen evolution reaction. So this is I0 for hydrogen on zinc surface. This is correspond to E equilibrium for hydrogen. Let us assume to be 0 voltage as per standard reduction potential series, and here it is E equilibrium for zinc, and this is also a standard reduction potential. Now let us say this is my I0 zinc on zinc surface. So I0, as you know, that this is exchange current density. Now if we follow the polarization plot, so this is my E core and this corresponds to I core. So zinc will corrode at the rate corresponding to current density at this point, which is a junction point. So let us extend this anodic part. Now let us see what happens if we increase the potential from that stable potential, so which is E core. So if we extend, so let us say I am here, I go to a new position, let's say this, another new position, let's say this. Since zinc is maintaining its active behavior, so that means as per Tafel equation, it goes on dissolving as we go the polarization on positive direction. So, this is anodic polarization. So, we see that dissolution rate corresponding to IA. So, these are all IA of zinc corresponding to zinc minus 2A 2 electron equal to zinc plus plus. So, zinc will keep on increasing its dissolution rate, and we have a greater and greater amount of zinc dissolution. So, we cannot have any protection. The corrosion rate cannot be reduced. So, this is basically happens when this particular behavior, that anodic polarization increased dissolution rate, just like what we have shown here in case of active metal in electrolyte. Now, let us see what happens if we have an active passive metal. And this is of course specific to composition of the metal plus specific electrolyte. Fine. Now, if we, let us say, in an acid solution, let us say H2SO4, steel shows active passive behavior. Okay. So, then I can have this very nature. So, this is, let us say, log I. Now, if the metal, let us say some metal M, we will show example later, and let us say it is H2SO4. Let us say this is my equilibrium of that metal. This is corresponding to I0 of that metal on metal surface, and if that metal shows active passive behavior, this is my active passive part. Let us say this is anodic dissolution, this is cathodic part for that metal. Let me just put it a little on the left side. So, we have hydrogen evolution reaction, it is the cathodic reaction. Let us say it is maintaining So, let us say this is the situation. So, this is the hydrogen evolution. So, let us say this is equilibrium, hydrogen. This corresponds to exchange current density of hydrogen on metal surface. The metal shows active passive part when you go for anodic dissolution or anodic polarization. So, that means if we go upward, the metal will show very such behavior. But we know as per mixed potential theory, if the cathodic reaction and corresponding polarization interacts with this anodic polarization part in the active zone, then that will be my E core. So, the E core here corresponds to this very point, and I core would be this one. And as we know that active zone is, so this is my I critical, and from I critical to the E equilibrium, this potential range is active zone. And the next part till transpassive zone starts, that zone is called stable passive zone. We will see later, that is the zone where we can also term it as protection zone. We will see later, protection zone, it can be considered as protection zone. And beyond that we have transpassive. Okay. Now, if we leave that system in the solution just like that, it will always have I core like this, what is actually indicated here. This I core will be followed and this will be my E core. And interestingly, if we do polarization, we will see that the polarization plot will look like this. So, in fact, how we get it, I will just draw it and then wipe it off. So, this part will extend. So, if we draw with this color, so this will be I have just drawn a little off from that black line. So, it will be almost on top of that line depending on the difference of IC and IA. So, this particular line corresponds to IC or the cathodic current density, and this is IA, and this experimental plot what we get, since this I is nothing but I applied, which is obtained by IC minus IA or IA minus IC, depending on where IC is more magnitude wise or IA is more magnitude wise. For example, below this particular E core, it should be IC minus IA, and that becomes my I applied, and beyond that line it will be IA minus IC, because IA portion is IA value is more than IC. So, that way we find I applied and take a log and then plot it. So, that should be the plot. So, now if we start doing anodic polarization, let us see what happens. So, anodic polarization will start towards this direction. Now, Let us say I go to this level, then I go to the maximum or the corresponding to I critical, because I am moving up. Then I go to this level, then I go to this level as I am moving up. So, my potential is gradually moving up since I am employing anodic polarization. So, let us assign some value. Let us say this value corresponds to 10 to the power 3 and this value corresponds to 10 to the power 4. This value corresponds to, let us say, 1. This value corresponds to, let us say, 10. Okay. Like that way, if we keep moving on, and this value corresponds to, let us say, 10 to the power minus 2. This value corresponds to 10 to the power minus 4, and this is in ampere per centimeter square. So, what should be I applied as we go up? So, if I try to locate those polarization point, let us say this is 1, this is 2, this corresponds to 3, this corresponds to 4. Now, in case of 1, what should be my I applied? Ten to the power 3 minus 10 to the power 10. So, it becomes fine. This will be my total current density required at point 1. If I stay here, if I stay at that polarization, this should be the current requirement. Let us say what happens at point 2. I applied would be 10 to the power 4, which is this, minus 1, because this is 1. So, it will be so that means if you see that the current density requirement is enormously increasing as we go up and stay at those locations 1.1 or point number 1, point number 2, all those points if you would like to stay. There is a huge increment in current density. Now, let us see what happens once we approach 3. I applied would be 1 minus 10 to the power minus 2, and this I applied here all the cases equal to I A minus I C, since this is I A, this is I C, and I C is negative because of its direction. So, that is what I am taking a mod value. So, I am just bothered about the values, magnitudes. So, now if I do that, so then 1 minus 0.01, so the value would become ampere per centimeter square, and so then point number 4 if I go, I applied would be 1 minus 10 to the power minus 4. So, this value, so this minus this, I am just giving all those locations so that it becomes clear to you. So, that way we have gone ahead and then found out those values. So, this would be 1 minus 0.0001. So, this is almost 1. Now, what will be dissolution rate at this location, which is nothing but IA, is 10 to the power 4 ampere per centimeter square. Here this is 10 to the power 3. Here in at point 2 locations it will be 4 ampere per centimeter square. Here it is 10 to the power, here it will be at point 3 location it is 1 ampere per centimeter square. Here it is also 1 ampere per centimeter square. Now, we could see that the current density corresponding to dissolution rate, which is nothing but IA, suddenly drops to a great magnitude to the level of 1 ampere per centimeter square from 10 to the power 3 or 4 orders. Once I take this polarization to the passive zone, and let us say I stay at point number 4. So, that means the material would, or the metal or alloy in that particular electrolyte will achieve passivity, and to maintain that passivity, or let us say I would like to stay there for longer duration, to maintain that position, that polarization, that particular very potential position. So, this position I would like to stay. So, then amount of external current I have to supply is of the order of 1 ampere per centimeter square. So, I have just given an example. So, this value would be of the order of milliampere. So, let us say instead of ampere I put milliampere. Okay. So, this is milliampere, even if it is milliampere, still 10 to the power 4 is a very big current density. Now, we could see that there is a enormous decrease in the requirement of applied current if we can take the potential to the stable passive zone and maintain there, okay, or position there for a longer duration. So, material would dissolve at the rate corresponding to this value, and which can be a very small quantity. Okay. So, this is the very principle of anodic polarization. So, here I could see that initial polarization will need a lot of current density. That means applied current density is huge. So, that means you have to supply a good amount of DC power or DC current. But once it takes to the passive zone, the current requirement to maintain that passive zone would be very minimal. It is of the order of 1 milliampere per centimeter square as per this particular drawing. So, you can actually, this particular value sometime it goes to few microampere per centimeter square. So, now you can sense that the current value would be, or let us say instead of milliampere, let me put it as microampere. So, let us say microampere. So, still it will be, if you see this value is quite large, but when you come to this value, it is a very small quantity, very tiny quantity of current we have to pass. But at the same time, so this is in terms of microampere. Okay. So, the 1 microampere per centimeter square, the corrosion rate is extremely low. So, if we achieve this particular position, so what are the advantage? I need corrosion rate would be order of 10 to the 1 microampere per centimeter square, and current requirement would be, so this will be all microampere because we have considering in terms of microampere. So, the current requirement would be nearly 1 microampere per centimeter square. Now, we could sense that by doing anodic polarization in case of active metal, I see that corrosion rate is increasing exponentially, because in the log scale will be increasing very large at a very large rate or large degree. But just like in case of zinc in HCl, but once we go to this particular situation, I can get a very good corrosion protection corresponding to the passive range by maintaining the position of the polarization at this location. So, it is better to position at a bit of away from this location where passivity starts, so that even if there is a little fluctuation in the current potential, it would not come back to this location. See, let us say there is a small amount of fluctuation. So, if this is the fluctuation in potential, maintaining that potential, still it will maintain its position in the stable passive zone. So, that is what this is called protection zone. Fine. So, this is related to anodic polarization and having protection, and this is only possible if it is active passive metal. Other way around is basically we are sending more amount of positive current or the line current to the metal side. So, we are actually maintaining it all the time anode. So, in this case the metal which is to be protected, metal is always anode. So, it and still it gives you protection or low current density due to maintenance of passivity. The difference between anodic protection, here also we need external power source. Fine. And initial polarization actually needs a lot of current, but after it achieves stable passive zone, then the current requirement would go down drastically. So, the difference between anodic protection, let us say cathodic protection. So, this is valid in case of active metal. It does not matter whether it is active passive or active metal. Since it relates to cathodic polarization. Now, here there are two situations. In one case ICCP, we need external power source, and here we need a constant power all the time, and the current requirement would be little higher than the current requirement for anodic protection when it achieves the protection zone. So, here current requirement would be higher than this once it achieves protection zone or once the polarization takes the metal to the protection zone. So, ICCP, it needs external power source, but sacrificial anode which also takes the potential of the metal which is to be protected to a lower value or cathodic polarization, here no need for external power source. fine. And both the cases this external power source should be DC or the direct current source. AC we cannot apply, because in case of anodic polarization we need to send positive current to the metal all the time. In case of cathodic protection ICCP, we need to send negative current or the electron to the metal for protection. So, we cannot switch the polarity. So, these are two basic difference as per our mechanism goes. We will discuss more on the how the arrangement is done and what are the situations where we should use anodic polarization, what are the situations where we should use cathodic polarization. Those will be discussed as we go ahead. But at least if we try to look at the anodic protection, where that can be possible in case of let us say a big tank holding acid, and if the power source is cheap. So, then definitely it is better to go for anodic protection, provided the metal shows active passive behavior and the passive zone corresponds to a very low current density. So, then my current requirement would be very low, at the same time material would show a fantastic corrosion protection. But cathodic protection on the other hand, since we have sacrificial anode, even if the power source is not available, then also this protection method can be employed, because here only what we need to do, we need to take an active metal piece and then connect it to the metal which is to be protected galvanically. Like let us say if you want to protect a sieve hull, on the sieve hull you just put zinc inserts. Okay. So, those zinc inserts will be tagged to the metal face, and that tagging would lead to protection, because the zinc will dissolve and it will supply necessary electrons for cathodic protection of that particular hull material, which is let us say steel. So, let me stop here. From next lecture onward, we will try to look at some of the examples, practical examples of cathodic and anodic protection, and also we will try to calculate anode efficiency, and that anode efficiency we will try to do it for let us say sacrificial anode. So, we will try to look at for zinc as well as magnesium how to calculate anode efficiency or anode capacity. So, those will be in the form of ampere hour per kg of the anode. So, that we will try to reflect and we will do some calculations. So, till then let me stop here. Thank you.